Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about maximizing area and introducing the concept of optimization. So let's jump right into a type of question I'm sure most of you have seen before. This is a pretty standard algebra question for middle school or high school, but let's take a look. Farmer Phil is building a rectangular pen for his pigs. He plans to use 16 feet of fence for the pen. What dimensions will give the maximum area of the pen? Right, so this is a fairly standard question. We have this amount of fence we want to use, and we want to give the pigs the largest area, the maximum area we can in this case. Now, to introduce the concept, let's rephrase this as an optimization problem. So the general idea of an optimization problem is that we want to maximize or minimize a quantity, and we are going to be subject to some constraints when we're doing this. So in our example, this is fairly simple, right? But we want to maximize the area, and we're subject to a fixed perimeter. So the perimeter is an exact value that we have there. Now, these constraints could be different, right? Maybe we can use up to some amount of fence, or maybe the fence costs an amount of money and we can use up to some amount of cost for the fence. Right, and so these are where you start to see how this might come up in a lot of different fields. In fact, in economics, business, right, you might want to maximize profit. You might want to minimize the costs of something. And then you're going to have all of these constraints about how much money you could spend, or how much time you have, or different logistical things that way as well. And that's where a lot of the applications come into play, but these are actually big questions in terms of computer science as well. There's a lot of different algorithms and ideas you can learn for solving these problems in general. Now, our question in particular is not too difficult of one, right? This is one, like I was saying, probably a lot of us have been comfortable with before. So we want to maximize the area. So when we see the area, well, the area we know for a rectangle, remember, is length times width. So we have our area is length times width. We have a fixed perimeter of 16. Now, where does the perimeter come from? Well, we can write this in terms of the length and width as well, right? The perimeter is equal to 2 times the length plus 2 times the width in this case. So we can start working with these numbers and the constraints we have from there. Right, well, this fixed perimeter of 16, right, this is really telling us that L plus W is equal to 8, 16 divided by 2. So this is telling us that, right, and we're going to do this kind of by substitution here. So maybe let's solve for W. W is 8 minus L. Then if we plug that into the area equation, right, the area is equal to length times width. But wait a second, we just said that the width is 8 minus L in this scenario. So now we have this equation here for the area. Now, skipping a little bit here, right, this is a quadratic. Right, so this here is a quadratic equation. It is a parabola, right? So the max, we know where the maximum occurs. You could expand this 8L minus L squared. The maximum occurs at, right, the B over 2A kind of stuff there as well. But in terms of the roots, we know this has zeros at 0 and 8. So the max occurs at L equals 4. So the max area is going to be A here is 4 times 4 is 16. So we can find our maximum area in that case as well. So however you find it, once you see that this is a parabola, things work pretty nicely for coming up with our answer from there. Okay. Now, side note, it's kind of fun. The perimeter is equal to the area, but that's not really relevant to our question here. So let's think about this in general. And this should remind us about inequalities. And in fact, the AMGM inequality is very, very relevant here. To remind us what this says, if we have a bunch of non-negative numbers, so no problem if we're talking about real world areas, lengths, and stuff like that there. If we have the arithmetic mean of these numbers, right? So let me highlight the name of this here, right? So AMGM, we have the arithmetic mean, the sum of the numbers divided by n. So that is our arithmetic mean. That is always going to be greater than or equal to the geometric mean. So geometric mean then here, the nth root of the product of those numbers there. So that's what we have in this scenario here. So just to write out some quick examples of this, right? And we'll see this on the next page too. But when n is equal to 2, right, we have the average of two numbers, a plus b over 2. This is greater than or equal to the square root of their product, a times b in that scenario. And, right, little bit of a hint for something that I'm going to ask you to do later, right? We could also do this for three numbers here as well. So just so we have different numbers, maybe let me use x, y, z. So x plus y plus z. Now we divide by 3. This is greater than or equal to the cubed root of their product x, y, z. So that would be what this says for three numbers in that case. So those two examples we could keep in mind for later things, either later in the video or for stuff I'm going to ask you to do as the question for the week. But first, right, let me mention this does have equality if and only if all of those numbers are equal. That should ring a bell a little bit with our square example, right? The L was 4, so the width was 4. We actually had a square for Farmer Phil, right? So let's try to look at this in general, right? So we want to maximize the area A of a rectangle subject to a fixed perimeter P in this case. So let's do this a little bit quicker than before. Right, so we know subject to a fixed perimeter P, we know, let me write it out here right away, P over 2 is equal to the lengths plus the width. Now it looks a little bit weird, but here we want the average of those two numbers to apply AMGM. So we could have P over 4, the perimeter divided by 4 is equal to the average of the length and the width. But now, where does our AMGM stuff come in, right? So AMGM here, right? So this is, let me kind of write this at the bottom here. This is our AMGM. So we have AMGM here. And we're going to have, right, this is equal if L is equal to W. So we know exactly when this is equal in this case too. So this is greater than or equal to, right, the square root of the length times the width in this case. But note that's equal to the square root of the area. So we have this equation here given to us in terms of, right, perimeter divided by 4 is greater than or equal to the square root of A in this case. So that's our formula here. And just for a little bit of cleanliness there, let me rewrite this in terms of, right, a squared and no square roots. So if I multiply by 4, square both sides, we're going to get to this equation that will look similar to something we have later on. but this is going to be p squared is greater than or equal to 16a for a rectangle here, right? And this is going to be equal for a square in this case. So we have our rectangle, and any rectangle, the perimeter squared is greater than or equal to 16 times the area, and it's equal if we have a square. Okay, so let's look then at one of the questions I'm going to have you do, and we will revisit next week. What about if we have a triangle? Now this is going to be similar. I want you to prove that an equilateral triangle has the maximum area of any triangle with a fixed perimeter. So you can think of this as our Farmer Phil question, except he's building a triangular pen in this case. Now it's a little tricky because now we have three variables. We have the three side lengths of the triangle. We don't have like a length and a width anymore. So let me give you a little bit of a hint. Well, you can use Heron's formula to calculate the area of a triangle in terms of the semi-perimeter. So that's already thinking about perimeter directly. And further hint verbally, probably you want to think about the fact that I gave you AMGM for three numbers in this case too. So you're going to need to use Heron's formula and use AMGM, and you can come up with a proof in this case. Now, in general, this type of thing does work. So if we have, right, four sides, we said it's a square, you're going to try to look at a three sides equilateral triangle. In general, regular polygons are going to have a maximum area. So if you're looking at a hexagon, among all hexagons with a fixed perimeter, regular hexagon is getting that. Now you may be wondering about, what about just in general? What if we're allowed to have curved sides or things like that? And the title, More Symmetry Equals More Area, probably gives away what's coming next. Among all the closed shapes, so if just in general we have some amount of fence and we can pretend the fence can be curved and stuff like that, circles have the maximum area given a fixed perimeter. Now this doesn't prove anything, but just to look at the example of the square we just did, right? Perimeter 16, a square has side length 4, that has an area of 16. A circle, then the radius, if we have a perimeter of 16, will be 8 over pi, and then the area is 64 over pi, which is a little over 20. So this would have a larger area in that example we're looking at. Now, that proof is much more difficult there, but I want to kind of get us thinking about the more advanced concept here, which is this idea of the isoparametric inequality. This gives a general bound for the area of a 2D shape given its perimeter. And there's a missing constant here. There's a missing thing here that I want you to try to figure out for next week's video. So what real number constant should fill in this blank? As a quick hint, well, remember we know circles. I just told you that circles have the maximum area for a given perimeter. So try to use that fact as an example fact to help you figure out this bound there. That, however, will do it for this week's video. If you liked, please hit the like button, give us a comment below, let us know if you have thoughts on the questions. Let us know if you have new ideas to share for the future, but we will continue this topic next week, so hope to see everyone then. Goodbye.